Hi, this is Jared Monhalley's video for the Simacogo game. So I'll start by simulating the gameplay. You select level first, so I can select level 4, and that's how many plies down the AI will search. Now I can select move. So if I choose 5, the console outputs the board, what it looks like, the scores below that, and the computer makes a move, it outputs the board again, and the scores again, and that will get updated on each round. So quickly playing the game for a few rounds, you can see the player is winning 7-2 on this relatively easy level. So now we'll move on to looking at, I won't play the whole game. At the end, it will display the winner and the final score. So we can go on to looking at the code. The main function, which I use to start the game, first prompt gives a little intro and prompts the user to select a level like we saw. And then the main loop of this is that while the game is continuing, meaning we haven't reached the full 81 moves, we oscillate between player turn and non-player turn. So this indicator gets flipped every time we go through a round. If it's a player turn, we just prompt for a move, validate that the move is valid, meaning that it is in a column between 1 and 9, and that that column is not actually full. If not, we continue to prompt them. Otherwise, we go to the computer move. After the game is over, throughout this we maintain a board. So the board is an object that knows how to print itself, it knows how to update itself with a move, it can validate moves or get the set of possible valid moves, and then it can score itself. So that board is a global variable in the main program that is kept throughout the game and continually updated. After the game is over, we'll get back to how the computer works, but after the game is over, when it knows that enough moves have been made, it decides who the winner is and outputs that to the console. So now let's look at how the computer makes its move, and we use the minimax algorithm for this, of course. I used a recursive algorithm, or a recursive function to model the algorithm, and I think it's best explained through an example. So let's say the user had chosen level 4. We'd pass in that level along with the board as it currently stands and some other variables that we'll see why they're used later to the minimax algorithm. This condition is the check for have we searched far enough down in our tree? Have we gotten to those leaf nodes? At which point we'll just want to start percolating that move back up. We'll get back to this later. But in the case of level 4, we wouldn't have hit that yet. So we'd say, all right, let's see if this is a max or min level. And you can use the depth to do that. Even depths are max levels. At that point, so this would be a depth of 0. We'd say, all right, this is a max indicator. Let's get the maximum move. The maximum move is we keep track of our max move, and given the current board, we say what are the next valid moves. So for each of the columns that you could go in that set of valid moves, let's skip the pruning for now. We'll get back to that. We create a new board object that's a deep copy of the original board, so we can safely update it with the next move that we're looking at without affecting the original board. Again, skip some of the pruning, and then we go down and we say, well, to get that next move, I want to recursively call the algorithm again to get me the move after that. Because you're not actually just looking at the current move. This is what gives us our depth first search, eventually gets percolated back up. So this next move that we're looking at is a product of the things below it. And eventually when that comes back up, we'll look at the score of that move and say, is it greater than our max move score? If so, we need to update that max move score, which is kept outside of this loop. So the recursion occurs, so next time we call that minimax high level pruned again, this time the depth will be increased by 1, so we'll hit our get min move. And that looks very similar. We won't go super into that because it's very similar to the max move, except it's finding the minimum thing of the nodes below it. Now for the pruning, in our get max move, at each round we say, is the max move that I currently have, if there's a beta above that that's less than or equal to that max move score, there's no reason in continuing the recursive search down our tree. We just return the current max move. We keep track of that beta throughout, and that's done down here. So in the max move, we're always keeping track of the alphas and updating those. So if at any point we either don't have an alpha set yet, or the max move is greater than our max alpha, we'll update that. Conversely, in the minimum, we're always updating the minimum beta. And the pruning occurs in the get min move because we're always looking if there's a max alpha that is greater than or equal to our current min move. That's it. Thanks for watching.